In this video, we'll talk about a new type of circuit element called an inductor, and the property that describes it called inductance. Now, an inductor is essentially a loop of wire. There are many different designs for them, but here I've shown two of them. Both of these are inductors, and they're both designed to produce back EMF. And the idea is that you want to produce a lot of back EMF. And the circuit element is going to try to mimic the fact that these are loops and try to draw those loops symbolically as these kind of hills, almost looking rounded hills, along the direction along the wire. So this here would physically stand for potentially something like this or something like this new thing called an inductor. Now, inductance is the property that an inductor has, and actually even a normal circuit will have a little bit of inductance, but this is the thing we're going to try to carefully control when we produce an inductor. Now, there's actually different types of inductance. The one we'll talk about here is actually generally referred to as self-inductance, which talks about the amount of EMF that's produced when the current in that circuit is changed. You can also have some EMF generated because another circuit has a changing current, and that's referred to as mutual induction. We will not we won't look at that phenomenon at all. We'll only look at self-inductance. So whenever I refer to inductance, I'll mean this inductance, self-inductance. And what it measures is the amount of back EMF you produce per rate of change of current. So if you're changing the current in your circuit by, say, 1 amp every second, you're going to produce some amount of EMF. And how many volts of EMF you produce per every 1 amp per amount of current per second that you're going on is your inductance. The symbol it has is a capital L. Again, this is one of those cases where there's no L's in inductance. I'm not sure why L is used for inductance other than we weren't using it for anything else really related. Now, it also doesn't mean angular momentum, which also sometimes is given as an L, but usually you don't do both angular momentum and inductance in the same problem, so hopefully it'll be clear when you mean one thing and when you mean another. The unit for it is called a Henry. 1 Henry is a volt times a second divided by an amp. A Henry is a particularly large amount of inductance. You don't usually see a Henry, you may see a picohenry amount of it. So this is a huge amount of inductance. So usually inductance is much smaller than a Henry. Now, to give a better conceptual understanding about inductance, it's sort of that inertia I talked about earlier of current, meaning how hard is it to actually change the current from what it is? How much does it resist this change? The larger the inductance is, the more it resists the change. The definition that they'll give for inductance, which is actually related to that previous ratio here. So one way you can think about it is it's this proportionality constant. That for a given circuit, there's a certain, if you have a certain number of amps per second changing, that'll produce a certain amount of voltage. If it's twice as many amps per second, then you have twice as much induced. And the proportionality constant is that the inductance. You can show that's also equivalent to this here, because if you actually relate what causes the back EMF uses Lenz's law, you can show that this here is an equivalent formulation of inductance, where it's the number of loops of your inductor, because this is again usually loops of a solenoid, times the change in flux, magnetic flux, divided by the change in current. So it's how much magnetic flux per amp of current changing do you get? Because as you change the current, you'll change the flux. Now, a common way of actually building this is to have a solenoid. And so, again, not everything is exactly, every inductor is built as a simple solenoid like this. There's usually some design that's similar to this, but since this is a very common design, and an object we've already talked about, we'll give you the inductance of this system. Sort of like we gave you the formula for the capacitance of a parallel plate capacitor. Parallel plate capacitors weren't the only way that you could actually build a capacitor, but they were one common way, an easy way of talking about it. Here we'll give you the formula for the inductance of a common, easy design of an inductor. So there's two ways you can write this that are analogous to each other. One is it's again this magnetic permeability of free space or vacuum permeability, that constant that shows up in a bunch of magnetic stuff, times the number of turns, so how many times did that wire get spun around, squared, times the cross-sectional area of that inductor, divided by the length of the inductor. That's equivalent to this same U naught times the number of turns per length squared, so that whole thing squared, and this again is sometimes listed on inductors, turns per length as a certain number, times the volume of the inductor. These are equivalent formulations. So you'll see you either use this one or that one depending what's more convenient, and this relates the design of the inductor to the actual inductance it has.